Welcome! In this series of videos, we will cover the design and implementation of a project, from initial design through coding and development to testing, using the PowerBasic Windows and Console compilers. Today we will amend our application to ensure all nodes have blockchain records for all transactions. In this project, there were 5 computers. One computer, Octal002, is monitoring what the other computers are actually doing. The remaining 4 computers or nodes are communicating with each other and carrying out transactions using UDP, the User Datagram Protocol. As this will be the last video in this project, I'll do a short recap of what we've achieved so far. The transactions between each of the nodes are captured in a blockchain record. This can be considered to be an audit trail of all the transactions, and each node has this audit trail. There is no central repository, which makes this a distributed system. Think of each block as being a parcel of data. Block 0 is the genesis block and is hard-coded into the system. The data within a block is boiled down to a hash value, comprising the block number, the timestamp, the actual data, and the previous block hash value. So each block references the previous one, forming up the chain. This makes retrospectively changing part of this audit trail especially difficult, as each block is dependent on the previous block, and all nodes hold a copy of the entire blockchain. So let's have a look at the code and finish off the project. As you will have seen in the previous videos in this project, there are 2 applications involved. The blockchain demo application, which sits on each of the nodes, and the blockchain demo monitor. This monitor is not involved in the actual transactions and has merely been created to allow us to watch what's going on. If we have a look at each of the nodes, we can see that following a series of transactions, each of the 4 nodes has created a demo blockchain text file. This is our audit trail of the transactions that have been carried out. If we have a look at the files that exist on the 2nd and the 4th node, we will see that the files are not the same. Currently, each node is maintaining its own audit trail of the transactions that it has been involved in. For example, the file for Odroid004 has transactions between Odroid 2 and Odroid 4. The audit trail for Odroid 2 has the transactions between Odroid 4 and Odroid 2 and Odroid 1 and Odroid 2. So each of the nodes only has transactions that involve it specifically. In order to make this audit trail complete, we need to have every node having a blockchain identical to every other node. There are 2 issues here. The first is the completeness of the audit trail. The audit trail needs to have a list of all the transactions done on all the nodes, and this file must be identical between nodes. The second is the timestamp. Currently, the timestamp is the time that the audit trail is actually updated on each individual machine. Regardless of how fast your computer's or network is, there is going to be a difference in the audit trail timestamp. This is because the receiving computer timestamps at the time it gets the transaction coming in. It will then confirm back to the originator of the transaction that it has actually recorded it, and at that point, the originator will then write to its own blockchain audit trail. We need to harmonize these timestamps. So let's have a look at the code in the blockchain application to see where we can do that. So let's have a look at the monitor thread function. As we're going to be harmonizing the timestamps, we'll need a new local variable to hold that information. And we'll call that variable timestamp. This will be a string variable. Within this function are a number of events. The event we're going to look at is the transaction event. This handles incoming transactions. So this will be received by a node to say that it's about to do a transaction, which has been originated by another node. This line of code is specifically checking to see that the incoming message is for this node. So in here, we're going to be receiving a new piece of data. We're currently pulling out from the incoming message a number of pieces of information. The first being the node that actually sent the transaction details, and we're then confirming that back to the originating node. So the new piece of information that will be coming in as part of the incoming message is the timestamp. This will be the timestamp that the sending node has actually stamped on the transaction. So we're going to pick this up and we're going to confirm back to the node all the details. So we're going to add to the confirm transaction function the timestamp. And having made that confirmation, we're now going to add this to the blockchain. So we're going to use a new function to format our transaction data into a form that will fit quite nicely into our blockchain audit trail. We'll create that new function in a moment. Next, we are going to add to the blockchain, passing it two parameters, the message details and additionally the current timestamp. And just so we can keep track of what's going on, we're going to create, for debug purposes, an audit text file. This will confirm that we've managed to add to the blockchain, or for some reason it has actually failed to add. So let's create this new function, format transaction data transaction. This function is doing a bit of reformatting of the data, and we're picking up the first, the fourth, and the third elements of the data, and we're passing this back to the calling function. So that completes the changes to the transaction event. We now have to look at the confirm event. This is where another node has confirmed that the transaction that this node has requested is now being processed. What we did previously was a straightforward add to the blockchain. What we're going to do now is, now that the transaction has been confirmed, we want to pick up the timestamp that came in on that message. So we're picking up the fifth element of the message, which is our timestamp. Next, we want to reformat our message so we can actually store it. So just as we did before, we're going to call a new function called format transaction data confirm. We'll create that new function in a moment. Next, we're going to add to the blockchain. As you saw earlier, the add to blockchain function has an extra parameter now. This is the timestamp. And we're going to add this to our audit trail as well. So this way we'll get this audit trail being added to for both confirmations and transactions. However, as we saw earlier, we're only adding to our blockchain for confirmations that this node has been involved in. We need to record all the other nodes as well. So we're going to put an else command in here and pick up the details from other nodes. This is going to be exactly the same piece of code, but will not involve a subtraction from this node's asset list. So we're going to be calling the new format transaction data confirm function. We're going to be adding to the blockchain with the timestamp, and we're going to be adding to the audit trail to confirm that the blockchain has been updated or not. So we now need to create the new function, the format transaction data confirm. This new function is going to be very similar to the one we did for the transactions. It's merely reformatting the data into a form that will appear in our audit trail. And to allow us to add to the audit trail text, we're pasting in from one of the other libraries a single function, the append to file function. As we've added another variable, in this case timestamp, to our confirm transaction function, we'll need to amend that function as well. It exists in the blockchain UDP library. So we've now added a new parameter to this function, the timestamp. And the timestamp is going to be the final element in the message we send off. So we mainly have to add it to the end of our UDP send command. Additionally, we'll need to add this parameter to our add to blockchain function, the timestamp. And further down the code where we actually populate the timestamp within the block, we're no longer going to call the get timestamp function. We're going to take what's been passed in the command line. This will synchronize all our timestamps. So now that we're actually populating the blockchain from the incoming message, we need to generate the timestamp at the point of the origination of the transaction. So within our monitor thread function, right at the beginning where we have the piece of code which raises a transaction, at that point we can actually populate the timestamp using the existing get timestamp function. And then in our raised_transaction function, we can pass the details of that timestamp to the system. So in our blockchain UDP library, we now have to amend the raised_transaction function to include this extra piece of information. And again, as before, we tack on the timestamp as being the last parameter in the UDP send command. So now that we've actually made these changes to our blockchain application, let's compile it and try running. It compiles quite cleanly. So we will blank out the data that's in all our Odroids. So we can start with a clean sheet. And we will copy over the new compiled executable blockchain demo to all those machines. Now we're ready to start running the system. We'll bring up the blockchain demo monitor first. And then we'll start on each of the machines the blockchain demo application. And there we have all 4 nodes responding back to say that they're now active. So all we need to do now is to wait for some transactions. Now that we've had a few transactions on the system, let's stop it running and have a look at the blockchain audit records. Here we have the blockchain records for Odroid number 3 and Odroid number 2. As you will see from the one at the top, which is Odroid number 3, it has the first transaction, which is Odroid number 2 selling to Odroid number 3. And the 2 transactions after that are for Odroid 4 selling to Odroid 1 and Odroid 4 selling to Odroid 3. And in the Odroid 2 audit trail, we have the same transactions with the same timestamps. If we look at the right-hand side of the audit trail, we can see that our blockchain numbers are identical in both audit trails. Therefore, we have managed to achieve synchronization between at least 2 of the nodes. If we look at the audit trail blockchain on Odroid number 4, we can see it has the same transactions, and the blockchain references are identical. This has been a very limited blockchain model, consisting of only 4 nodes. One of the problems with any system employing a blockchain system whereby each node must have the same record, the same blockchain as every other node, is keeping them all in sync. However, although this has been a very limited demonstration, it does show the fundamentals of the blockchain, a distributed system to keep track of transactions across multiple nodes. Perhaps you can find some use for some of the code within this application. But that's it for today. Thank you for watching.